In this video, we're going to talk about function analysis. We're going to do this for 2 weeks, so there'll be a second video coming up. The idea of function analysis is to use calculus to understand the key features of a function, or the key features of the function's graph. Things like increasing and decreasing, and concave up and concave down, and local min and local max, and inflection point. All those things that you talked about in pre-calculus, but you didn't really have a good way to find those except just by eyeballing it from a graph. And a graph can be misleading or incomplete, so we want to use calculus to make sure we have a complete graph that shows all the important features. So here's an example to show why we might want to do that. So let's look at these two graphs here. See if I can get them both on here. This looks sort of like a parabola, which would be, quadratic, even degree. This looks more like odd degree polynomial, maybe a cubic. And the issue here is that both of these graphs are graphs of the same function. And it's not immediately obvious. If I showed you the formula for them, you would see that. If you click on the little arrow here, this is a cubic, and it's the same one being plotted in both of them. So if I showed you the formula, you would know that this is not a complete graph. You know from pre-calculus that a cubic doesn't look like this. This looks like even degree because the end behavior is both tails point the same direction. And with odd degree polynomials, the two tails should point in opposite directions, like in this one. But that's fine with polynomials that you covered quite a bit in pre-calculus. But if you have a more complicated function that you don't already understand, how do you know, when you look at this first graph, how do you know that it's incomplete, that there is a place where it turns around and starts heading down? It looks on this graph like it has one x-intercept, and then from this graph we can see there's actually two. From this graph it looks like it's decreasing, changing to increasing, and that's it. And from this graph we can see it goes increasing, decreasing, increasing. So we want to use calculus so we can understand some of the key features of the function before we graph it to make sure our graph is complete and shows everything. So to apply calculus to this function analysis, we need to talk about critical points. And you should have covered some of this in the lecture. Remember that the sign of the derivative, f prime, is related to the direction of f. And by direction I mean increasing or decreasing or possibly constant. So if f prime, the derivative, is positive on an interval, then the original function f is increasing on that same interval. And if a derivative f prime is negative on some interval of x values, then the function f is decreasing on that interval of x values. So if the direction of f changes, so if it changes from increasing to decreasing or vice versa, then you have to have a change of sign in f prime. If f prime changes sign from positive to negative or negative to positive, either way, it either has to go through 0 or it has to jump over the x-axis. So either the derivative will be 0 at that point where it changes sign, or it'll have a place where it's undefined when it jumps over the x-axis. So a critical point of a function is some element of the domain, so this is an x value, an input, where the derivative is either 0 or undefined. Those are the places in the domain where the function might change direction. Now, it doesn't necessarily change direction there, but it could. It's also possible a function could change direction at some place where there's a gap in the domain. Like if there's a vertical asymptote, there's a gap in the domain there, and it could change direction at the vertical asymptote, or if there's a hole or something. But critical points give us the possible locations of local minima and local maxima for the function, because if you remember the definition of local min and local max, the direction of the function is going to change there unless we're at an endpoint of the domain. Okay, so note that the critical points are possible points of direction change. It does not necessarily mean the direction changes there. So we have to decide, given these critical points, does the direction actually change? And there's a couple ways to do that. One way is to look at the graph and see, does it change direction at that x value? The other way would be to try some nearby x values and see if the sign of f prime actually changes. So the derivative might be 0, but it could be positive on both sides of that 0. That's possible. So we need the sign to change, not just equal 0 somewhere. Now, 1 is sort of less work. You just look at the graph. The disadvantage of the graph is that we're not sure if the graph is good enough to see whether the direction changes. The whole point of this is we're trying to create a complete graph. We don't have that yet. This is all part of the process. So rather than go through all the work of getting a complete graph to make sure the direction changes, we're going to use 2. And we're just going to try some x values close by and see if f prime changes sign. Now, f prime, the derivative, is a function itself, and so it has its own critical points. So the critical points of f prime are x values in the domain of f prime, where f double prime, which is the derivative of f double prime is either 0 or undefined. The critical points of f prime tell us the possible locations where f prime can change direction. And what does the change of direction of f prime have to do with the original function f? It has nothing to do with the direction of f, it has to do with concavity of f. If f prime is increasing, then the original f is concave up. And if f prime is decreasing on some interval of x values, then the original f is concave down on that interval. Since the direction of f prime, increasing, decreasing, corresponds to the sign of its derivative f double prime, so f double prime positive or negative, we can rephrase that in this way here. If f double prime is positive on an interval, the original f is concave up, and if f double prime is negative, the original f is concave down. F prime can change direction only at its critical points, so f can change concavity only at the critical points of f prime. Okay, not the critical points of f, the critical points of f prime. That is, the critical points of f prime, or the places where f double prime is 0 or undefined, are the potential inflection points of f. Not necessarily inflection points, but potential inflection points. To see if it's an actual inflection point, we could look at a graph, or we could try some nearby x values. And again, the graph is not the best way to go, especially with concavity, because it's often hard to see changes in concavity. You have to play with your viewing window sometimes to see the change in the bend from concave up to concave down. So option 2 is what we're going to do again. We're going to plug in some nearby x values into f double prime and see if there's an actual sign change at that x value where f double prime is 0. Okay, so summarize that. We're going to have a function f. We're trying to analyze it. We're going to compute its derivative. We're going to find out where the derivative is 0 or undefined. We're going to calculate the second derivative, and we'll find where the second derivative is 0 or undefined, and we'll make sure that all those x values and their corresponding y values are on the graph that we produce. Okay, so let's do an example. Suppose we want to understand the shape of this function. Now this is a cubic polynomial, so just from pre-calculus we could do a good job with this. But let's go ahead and apply calculus and see how it works. Here's the default graph just to see why calculus is going to help us out. So I could, if I want to just play with the window until it looked better, but I know this graph is incomplete for a cubic polynomial. Cubic polynomial with positive leading coefficient. This side needs to point down, which it is, but this side needs to point up, which it's not. So I know, just from pre-calculus, that this has got to turn around over here somewhere and then shoot upwards. But let's go ahead and do calculus so that we can save the trouble of just manipulating the viewing window. Plus, and more importantly, that this is just an example of the steps involved. Cubic polynomial we understand from pre-calculus, but there's many functions that we don't understand from pre-calculus, and we're going to need to use calculus to understand them better. Okay, so first off, we need to find the domain of the function. That's going to matter. So in this part 1, we're just going to have domain all real numbers. In the next lesson, function analysis part 2, we'll talk about functions that have gaps in the domain, where you got holes or vertical asymptotes to deal with. Okay, so none of those today. Today, all real numbers in the domain. Step 2, calculate f prime. In Sage, as normal, I'm going to call this df for derivative of f. So I calculated the derivative of f. There it is. I went ahead, so this calculates the derivative of f and assigns it to this df function. Remember, this, when you have an equal sign, it doesn't produce any output. So that's why I added this little line here, df. That's what actually prints it out. And the only reason I want to print it out is to check its domain. In step 3, I want to find out where f prime is 0 or undefined. So I need to know the domain of f prime. And there's no issue here. It's domain all real numbers. But it is possible for the domain of f prime to be smaller than the domain of the original f. So we need to kind of check that. For today, all we need to worry about is where the derivative is 0. So I'm going to have Sage solve that for me. I'm going to ask solve derivative equal to 0, and it tells me. Now if the solve command doesn't work, you might have to use find root at this stage to find out where the derivative is 0. Okay, so two places where the derivative is 0, x equals 0, x equals 2. Those are the critical points of f. Those are the places where f might change direction. Now I want to see if f actually does change direction, so the next step is to choose some x values that are close to these and see if the sign of f prime actually changes. So let's start with x equals 0. I'm going to choose some x values nearby. So I chose negative a tenth and I chose positive a tenth. One of them is to the left. First one's to the left of 0. The second one is to the right of 0. And here's the outputs from the derivative. Okay, this is the derivative, not f. I don't care what f is. I'm looking at the derivative. The derivative changes from positive to negative. That means it changes from increasing to decreasing. So the graph is going up, and then it changes to decreasing. So I don't know if you can kind of see my little cursor as I draw that. Positive derivative to negative derivative creates a little mountain. It's a local maximum. So the function f, the original f, has a local maximum at x equals 0 because f prime changes from positive to negative at x equals 0. Now I said I want to choose something to the left and right of 0 that's relatively close by. Comment here is how close does it need to be? It doesn't have to be really close. The only condition is that you can't go past any of the other critical points. So the other critical point is 2. When I choose something to the right of 0, I have to make sure I don't go to 2 or beyond. I can't choose 3 or 10 or something. 2 is my boundary. I can choose 1. I can choose 1.9. It doesn't matter. Anything between 0 and 2, as long as you don't go past 2. To the left of 0, I could choose anything I want at all because there is no other critical points to the left of 0. But you might as well just choose something close. You don't have to think about it too much. If your critical points are really close together, then you'll have to worry about that a little bit more. Now let's see if the sign of f prime changes at x equals 2. So I chose something to the left of x equals 2. I chose something to the right of x equals 2. The sign changed from negative to positive. So the function goes from decreasing to increasing. So here's the shape. Decreasing changes increasing. Can you see when my cursor moves, I make a little valley or trough. So I have a local minimum. So at x equals 2, the original function f has a local minimum. Now you may have noticed I've been a little redundant here because this value to the right of 0 is to the left of 2. And so I could have used this same value in both of these. And I got a negative derivative to the right of 0 and of course a negative derivative to the left of 2. I'm being a little bit redundant by redoing it. Part of that is because it's just too hard on the computer to put a number line and make it all organized. And so rather than worrying about missing something, it doesn't take very long to just redo this calculation and I don't have to think about it. But there's a little bit of redundancy built in here. Alright, step 5. I'm now ready to talk about the second derivative and inflection points. So here's my second derivative. I call it d2f, or second derivative. You can call it whatever you want. Nothing special about the name, as long as you keep track of the name. I went ahead and just did the second derivative of f. Remember how to do second derivative. Here's the function we're taking the derivative of. Here's the variable with respect to which we're differentiating. And then finally, this is the order of the derivative, so second derivative. It's also possible, like I said, to do the first derivative of df. Remember, df is f prime. So this is the derivative of f prime. You can do it either way. Remember, this definition doesn't produce any output, so I typed d2f, so it will produce the output. Again, the only reason I produced that is so I can look and see, does it have any domain issues? And it doesn't, so we don't have to worry about that. So f double prime is never undefined. I just need to find out where f double prime is 0. Those are the potential inflection points. So step 6, I asked Sage, tell me where the second derivative is equal to 0, and it found one solution, x equals 1. So that's a potential inflection point. To see if it's an actual inflection point, I'm going to check and see if the sign of f double prime actually changes at x equals 1. So I took something to the left of 1, I took something to the right of 1, I fed that into f double prime, and the sign did change from negative to positive. So there is an inflection point there to change from concave down to concave up. Okay, now I'm done with the derivatives. That's the calculus part. Step 8 is the pre-calculus step. Find x and y intercepts. And so I asked to solve the original equation. Where is that equal to 0? And I got two x-intercepts, x equals -1 and x equals 2. And again, if Sage is not able to solve this equation, you might have to use the find root command. Go back to the solving equations lab. That was, I think it's week 2 or something, if you need to review that. The y-intercept is f of 0. As long as 0 is in the domain of the function, it has a y-intercept, which is f of 0. So here the y-intercept is 4. All right, step 9, think about the end behavior. And that's the limit as x goes to infinity of the function, and the limit as x goes to negative infinity of the function, provided that those make sense in the domain, which they do here. So here's the first one, limit as x goes to infinity. Here's the second one, x goes to minus infinity. See, the first one is positive infinity, the next one's negative infinity. That's what we expect from this cubic polynomial. If one of these limits is a number, then you have a horizontal asymptote at the horizontal line with that value. So if this first limit were 10, you'd have a horizontal asymptote at y equals 10. Or if this were 8, you'd have a horizontal asymptote at 8. It's possible to have two horizontal asymptotes, one at each end, though most of the functions we'll see will just have one, if any. Okay, now step 10, we're ready to make an informed graph. We want to have the x and y intercepts on the graph. We want to have the local min and local max. I'm not sure why I changed from local to relative here. Same thing, relative max, relative min, and inflection points. We want to have all those there. I'm going to actually mark them with a dot on our graph. I would suggest when you do this, you might actually have a piece of paper and write down the critical points. So the places where f prime was 0, that was 0 and 2. Where f double prime is 0, that's x equals 1. And write down your x and y intercepts. There's the x-intercepts. You might just have you don't want to have to scroll back and forth in this huge worksheet. So you might just jot down some notes to yourself. Where is there local maxes and mins, where there's inflection points, so you can have them all in one place. You don't have to scroll back and forth. But anyway, these are the ones we have here. 0, 1, and 2 are the critical points, and -1 and 2 are the x-intercepts. I want to find out what kind of y values I need for these x values. So I'm going to plug these x values into the function. So there it is. Now you don't have to plug in the x-intercepts because you know the function value is 0 there. That's the whole point. I did f of 2 just because it was one of the critical points. It happens also to be one of the x-intercepts, so that was kind of a redundant calculation. But I did that just for the sake of completeness. The point of this step is to plug in the critical points, the x values, so that you get the y values to go with them. Give you some idea of how big of range you need on your y-axis. Okay, so I need my x-axis to cover all of these numbers. So from -1 until 2, that's this interval. I need my y-axis to cover all of these numbers, so 0 to 4. Now probably you don't want to have your viewing window be exactly those intervals, because that puts critical points right on the edge. You don't want to be right on the edge. So you probably want to go a little bit bigger than that, just so we can see those points clearly. And of course, you can always adjust it later if you don't like how it looks. So here was my bare minimum in the x direction, so I went just a little bit more. I went down to -2. Oops. And I just changed that, sorry. And my bare minimum x value, or maximum x value, was 3. Sorry, it was 2, and so I made it 3. And in the y direction, 0 to 4, I went out a little bit bigger, -1 to 5. Okay, I added on plots of these points, Now, when you have several points to plot, you can either do a separate point command for each one of them, but that's a lot of typing. So instead, you can just use one point command. And if you feed it a list of points, you can plot all the points at once. And the way you give it a list in Sage is square bracket. So this parenthesis is the parenthesis for the point command. It starts there. This is the end of the point command right here. This bracket starts a list of points for it to plot. So square brackets around your points. And then these parentheses are the parentheses for the ordered pair. So this is the ordered pair, -1, 0. That's this x-intercept right here. 0, 4, that's the y-intercept right there. 1, 2, that's the inflection point. And 2, 0 is the x-intercept. This is also the local min, and the y-intercept is also the local max. So there's a lot of overlap between these different features in this particular function. Feel free to, you can just copy and paste this if you want, then just change the numbers here in these points for your assignment. I like to use black and size 20. If that's too small for you, you can make it bigger. This size will change the size of the dot. And if you want a different color, that's fine. You can change the color of the plot of f too if you want to. Okay, now this is a complete graph of this function. It shows the x and y intercepts, it shows the local mins and local maxes, it shows the inflection points, it shows the end behavior, so we can see everything we need to see. It shows where this is increasing and decreasing and concave up and concave down. Now that we have a complete graph, the last step is to talk about the key features of the function. So if there's an absolute max or min, or global max or min, whichever word you like, as opposed to just relative or local that we've talked about already. Intervals where it's increasing and decreasing, and intervals where it's concave up and concave down. Okay, so I look at the graph. There is no absolute max because remember the end behavior is this just goes off to infinity, so there is no top to this function. It just keeps getting bigger. There's no absolute min because this just keeps going down, 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 down. The increasing, so from negative infinity up to 0, it's increasing. Okay, that's this part. Remember when I ask where is it increasing, I want an interval of x values. So this is the part of the graph where it's increasing that corresponds to x starts over here at negative infinity, stopping at 0. From 0 until 2, it's decreasing. So as x goes from 0 to 2, the function is heading down. And then from 2 to infinity, on the x-axis, the function is heading up. So increasing negative infinity to 0, decreasing 0 to 2, increasing 2 to infinity. Now technically you can include these endpoints here, but I don't care if you do. If you want to put you want to put parentheses there, your pre-calculus teacher may have only used parentheses depending on how they define increasing and decreasing. Don't worry too much about that. So if you just want to put parentheses, that's fine with me. But if you want to put the square brackets, they are actually correct here. Concave up and down. So this thing starts out concave down on this part. Remember what concave down means. If you lay your hand along this curve, your palm will point down. So I can't show you that on the computer screen, but anyway, this is concave down. And if you put your hand around this curve, your palm will point up. So that's concave up. So concave down from negative infinity up into the inflection point. The inflection point is at 1. Now we know that because that's where the critical point of f prime is. F double prime is 0 at x equals 1. That's our inflection point. In pre-calculus, you would just kind of eyeball this and say, okay, well, it looks like it's 1. And you wouldn't know for sure. But now that we have calculus, we can figure out exactly, as long as we can figure out exactly where f double prime equals 0, we can figure out exactly where this inflection point is. And so negative infinity up to 1, it's concave down. From 1 to infinity, it's concave up. And that's what we have here. Notice that the endpoints here for increasing, decreasing, the 0 and the 2, those are exactly the critical points of f, places where f double prime is 0. And the endpoints here of concave up and down, which in this case is just 1, that's the critical points of f prime, places where f double prime is 0. So don't get those two confused. Don't put the places where f prime is 0 in here in concave up and down. Okay, that doesn't have anything to do with f prime being 0. This has to do with f double prime. And don't put these inflection points up here in my increasing, decreasing. Okay, try to keep those things separate. All right, we'll do one more example. This one will go a little bit quicker. So I look at here's the default graph of this function. It looks like an exponential function. If you have in your mind an exponential function, you're like e to the x. This is the general shape. Horizontal asymptote along the x-axis here, and then as x goes off to infinity, the function just rockets up. Now, it almost looks like the x squared here has no relevance at all. This looks like e to the 4x. And this graph is actually misleading. There is a little wiggle in this graph, which you can't see. And so we're going to go ahead and analyze this with calculus. Domain, all real numbers. Calculate the derivative. Find where the derivative is 0. There are 2 places. Those are my potential inflection points. No places where the derivative is undefined, so these are the only critical points. I want to see, does the sign of f prime actually change at these 2 numbers? So I chose something to the left of negative a half. I chose something to the right of negative a half, and I saw there was a sign change. It changed from positive to negative. That means the original function goes from increasing to decreasing, and that's a peak, so local max. By the way, I would recommend that you choose something to the left and choose something to the right in that order, so that you make sure you get this. We normally move from left to right. Positive changes to negative, increasing changes to decreasing, so you get your peak. All right, something close to 0. There's to the left of 0. There's to the right of 0. Did the sign change? Yes. From negative to positive, the function goes from decreasing to increasing. That means there's a local min at x equals 0. Find the second derivative. Here's the second derivative. No domain issues. Critical points are just where the second derivative is 0. I got 2 answers. There's the exact values. So here's one where you're not going to see those exact values from any graph. These are irrational numbers. So if you want to know exactly where the inflection points are, you can use that, solve where the second derivative is 0. And these are the exact values if you want to know. Now, we don't really care about the exact values right here. We're just trying to produce a graph. So let's go ahead and convert these to decimal. So I just copied and pasted these numbers from here and used the capital N command to convert to decimal. And these are the 2 answers, roughly negative 0.85 and negative 0.15. So I'm going to choose something to the right and left of each of these. Left first. Left of negative 0.85 to the right of negative 0.85. Did the sign change? Yes, positive and negative. There is an inflection point at that value. All right, now we'll try x values near the second one. All right, so I chose something to the left. I chose something to the right. Did the sign change? Yes, negative changed to positive. So there is an inflection point at that value. Okay, I have my inflection points. I have my local mins and maxes. I am now ready to do x and y intercepts. There's one x-intercept, x equals 0. That's also the y-intercept. So the origin is the x and y-intercept, both. Now the end behavior, this was the only thing really, of all the above steps, the end behavior was the only thing that was clear from that original graph I showed you. As x approaches infinity, the function goes off to infinity. As x approaches negative infinity, the function goes to 0. That means the x-axis is a horizontal asymptote, at least in the negative direction. Okay, step 10. Let's make our informed graph. So I have the x values I need, these critical points, along with the x and y intercepts, and I'm going to plug those into the function to see the y values that go with them. Okay, these are the y values that go with my inflection points and local min, local max. And you can see now why this original graph didn't show those things. If we go back up here to the original graph, notice what the y-axis is, from 0 to 50. That's because this function grows very rapidly here. So when x is 1, this is e to the 4th power, which is a pretty big number. So from 0 to 50, I can't see the inflection points and local mins and maxes because all of those happen between 0 and 0.03. So the main features of this function are happening between 0 and like 500ths. And the original graph went off to 50, so no wonder I couldn't see anything. So here's my graph. Notice that my y, or my x min and max, I went from minus 1.5 to 0.5. So this was the lowest I needed, and the 0 was the biggest. So again, I went a little bit to the left of the lowest one, and a little bit to the right of the biggest one. And then in the y-axis, it goes from 0 up until 0.03 something. So I didn't go below 0 because this function never goes below 0. 0 is actually the absolute minimum. So I started y min at 0. The y max I put at 0.05, a little bit past the 0.03 that I needed. And then of course I added those points in. I went ahead and used the rounded values for these guys, so I didn't type in the entire thing. If you want, you could copy and paste the whole thing and get a little more accuracy. There might be, if you round too much, you might see that the dot is not exactly on the curve. It might be a little bit off-centered. It's not really that big a deal. So up to you kind of how many decimal points you want to include here in these points. Here, I didn't bother putting the exact values, I just rounded them. Okay, so this whole little wiggle in the graph was not visible from that original graph that I did from -1 to 1 when y went from 0 to 50. Now, this little wiggle might not be important in whatever you're doing. It depends on the application. But in some applications, this little wiggle might be the most important thing of the whole graph. And so, calculus showed us where we should be looking. So rather than zooming in and out forever and hoping for the best, calculus tells us exactly where to look to see these important features. All right, is there an absolute maximum? No, because this function just keeps going up, up, up. Is there an absolute minimum? Yes, right here. The absolute minimum value is 0 when x equals 0. And increasing, decreasing, so the function is increasing at the beginning, right here, until it reaches this peak. That's at -0.5, so from -infinity up to -0.5, it's increasing. From -0.5 to 0, it's decreasing. And from 0 off to infinity, it's increasing again. It's concave up at the beginning. Okay, notice how this is bending upwards. This is the inflection point at -0.85, roughly. From there, it's concave down until it reaches the next inflection point at roughly -0.15, and then it's concave up again. So concave up from -infinity to the first inflection point, concave down between the two inflection points, and then from the second inflection point on, concave up again. And again, notice how the places where f double prime is 0 shows up in these answers for concave up and down. The places where f prime is 0 shows up in increasing, decreasing. Okay, there's another reason why I recommend you write these all down. Write down f prime equals 0 at these 3 numbers, and f double prime equals 0 at those 2 numbers. So when you get to step 11, you'll have those numbers written down. You won't have to guess from the graph. I mean, -0.5, that's not that hard to see. But this one is like, what was that again? If you have it written down, you won't have to scroll back up and figure it out. All right, so your assignment has 2 problems. I'm going to work through the first one in class. So you're free to do it on your own if you want to. But if you want to just wait for class, I'm going to go through with you step by step the first problem in your assignment, and then the rest of the class you can work on number 2.